Hi, my name is Alex, and my team members are Jacob, Matthew, and Ellie, and we're Team Beat Me, I'm Scotty, and today we'll be demonstrating the concepts of work and energy using a pulley system. The concept of work is just force times displacement, and this will be demonstrated through our system.
So today we are going to be using a system of 3 pulleys and 2 masses to demonstrate the concepts of work and energy and how to relate them using energy equations. As you can see, we're going to have a mass A and a mass B. Mass B will be supported by a single line. Mass B will be supported by 2 strings right here. They will be of equal length. Mass A will start at a certain height from the table, and then they will end at a different height, a much higher height, and then mass B will start at a certain height, and it will end at what we're calling the position datum. It will end at essentially 0. Our lengths are going to be measured from the top, and they're going to extend down to a certain distance.
Okay, so this is the basic equation that we're working with. It is V1 plus T1 plus work done by non-conservative forces equals V2 plus T2, where the V's are our potential energy due to gravity, and our T's are our kinetic energy. Now for this bit, we are assuming no conservative forces. We're assuming that no friction or air resistance is acting on the system. Therefore, this term goes to 0. Also, both masses start at a 0 initial velocity. Therefore, this term goes to 0. We know that V1 is going to be MGH1 for mass A and MGH1 for mass B added together. V2 is going to be MGH2 for mass A and no mass B, because mass B at that point will be at the bottom of the data and therefore have no potential energy due to gravity. The kinetic energy at the end is going to be the sums of 1/2 mv squared for both masses. So we combine these all into one equation. We do a little bit of simple but tedious algebra, and we get this master equation, VB equals all of this right here under the square root. Therefore, we were able to calculate that our velocity should be somewhere around 1.2796 meters per second.
So this is our mechanism here. We have mass B, this is our mass B, and this is our mass A. The way it works was that we had the starting position as so that mass B was above mass A. At this state, we would have potential energy in mass B that would then create the negative work from mass A as it fell through, as such. At this state, it would demonstrate the way that work energy flows through our system. So with our system, we measured the velocity of mass B using the ultrasonic sensor, which then sent the data to our spreadsheets on our computer. So that takes care of the velocity part. And we measured our initial and final positions of mass A for our calculation formula using the ruler here.
I'm Matthew, and we're now going to discuss our results from our experiment. So the experiment that you saw Ellie run, we ran that experiment 10 times, and we found the max velocity and log pro from each run. We then took our 10 measured velocities, added them together, and averaged them to get out our measured velocity average, which is 0.8290 meters per second. Now, we then compared that to our calculated velocity, which is 1.28 meters per second, and there was a large percent error, 54.5%. Now, some of this error can be accounted for because we did not, in our original equation, take into account that there's work done by non-conservative forces, namely friction. So, in order to account for this, we went back and redid, we used our measured velocity here, and we found the work due to non-conservative forces, which is work due to friction. So, the calculated work due to friction, or non-conservative forces, is negative 0.0634 joules of energy. If we included this work back into the original equation, we'd get out our measured velocity. So in our experiment, we took a look at work and energy and how we can relate potential and kinetic energies in order to find our velocities in relation to position. We could have approached this experiment a different way using Newton's second law of F equals ma, and we could have done free body diagrams on each pulley and block and used our kinematics and kinetics equations in order to solve for velocity. That, though, would have been a lot more complicated than our simple and elegant work and energy formulas here. Thank you very much.